Interference patterns of light can be seen in a double-slit experiment. When light waves bump into each other, they can interfere constructively or destructively. When they interfere constructively, they are interfering in phase. The peaks line up with each other and the troughs line up with each other for an overall additive effect, where the result is a combined wave with tall peaks and deep troughs. It is like having a +1 combined with a +1 to make +2, and a -1 combined with a -1 to make -2. When they interfere destructively, they are interfering out of phase. Peaks are lining up with troughs for an overall subtractive effect, where the result is basically a flat line, no wave. It is like having a +1 and a -1 combined to make 0. In the double-slit experiment, constructive interference makes the light more intense, so there are bands of bright light. Destructive interference gets rid of waves, so destructive interference corresponds to the dark bands. We see an alternating light-dark pattern of interference. Standing waves are anchored at endpoints like a guitar string. Standing waves exhibit quantization. Only waves with integer numbers of half wavelengths are able to form. A half wavelength is like a peak or a trough, but not both. Standing waves could also contain nodes, which are regions of the wave other than the endpoints that are not in motion. It's like the guitar string is vibrating up and down, but a particular point stays still. The number of nodes is one less than the number of half wavelengths. The top wave in the figure has one half wavelength and 0 nodes. The next wave down has 2 half wavelengths and 1 node. 3 half wavelengths would have 2 nodes, and 4 half wavelengths would have 3 nodes. Standing waves are one-dimensional. Waves can also be two-dimensional, as seen in this figure. This machine vibrates at a certain frequency, causing sand to gather at nodes. These nodes could be radial or angular. Radial nodes have constant radii, but all angles, so they end up making circles. All 4 parts of the figure have radial nodes. Angular nodes have constant angles, but all radii, so they end up making lines. The bottom 2 pictures show angular nodes in addition to the radial nodes. These figures are going to be important for helping us understand electron orbitals later in this chapter. The intensity of sunlight at different wavelengths has been measured and found to be greatest in the visible region of the spectrum. That works out well for us, since that is what we are able to see. There is a steep drop-off in intensity in the ultraviolet region, but a more gradual drop-off in the infrared region. This curve matches up with the model for blackbody radiation at 5,250 degrees Celsius. Blackbody radiators all have the same shape of a curve, a steep drop-off at shorter wavelengths and a gradual drop-off at longer wavelengths. The height and peak of the curve depend on the temperature of the blackbody radiator. At higher temperatures, the peak is more intense and shifted to shorter wavelengths. If classical mechanics were sufficient to describe the universe, it would be expected that the intensity would always increase with decreasing wavelength. However, the experimentally measured drop-off in the ultraviolet region, sometimes called the ultraviolet catastrophe, does not match up with classical mechanics. Blackbody radiation was only able to be correctly modeled if energy was assumed to be quantized, having certain allowed discrete numbers. This is one of the initial experiments that led to the discovery of quantum mechanics.